Even in this video we are going to understand what is a t-distribution. So let's say we have two random variables which are independent of each other, x and y. X is normally distributed with mean 0 and standard deviation of 1, and y square has a chi-square distribution with n degrees of freedom. So those who don't know what chi-square distribution is, so chi-square distribution with n degrees of freedom is the distribution obtained when we add squares of n standard normally distributed random variables. What does that mean? That if we pick n IID random variables and add their squares, then whatever distribution we get is, we call it as chi-square distribution with n degrees of freedom. So here Zi is a normally distributed random variable with mean 0, standard deviation 1, and all these Zi's are IID. So in this case, when x is normally distributed with mean 0 and standard deviation of 1, y is chi-square distributed with n degrees of freedom, then this expression, then the random variable x upon root y by n, we've called that this distribution, whatever the distribution of this random variable is, to be a t-distributed random variable with n degrees of freedom. So basically t-distribution looks like this. So it is a symmetric distribution, and with mean 0, and it looks like a normal distribution, but it's not exactly normal distribution. So a normal distribution would look like that. But as degrees of freedom for t-distribution increases, let's say here the degree of freedom is 3, let's say we make degrees of freedom 10, it reaches more and more closer to the normal distribution. So let's say degrees of freedom is 30. So as we increase, so finally for a very large degrees of freedom, it would be almost normal distribution. So it would reach normal distribution as we would increase degrees of freedom. So let's say this is for 50 degrees of freedom. So mean for t-distribution is 0 and variance for t-distribution is n upon n minus 2, where n is degrees of freedom. And next thing we are going to do is we will calculate the probability density function for this t-distribution, and we'll also calculate the expression of variance and mean for the t-distribution using the probability density function. So let's go. Now let's try to calculate the probability density function for the t-distribution. So to calculate the PDF for t-distribution, let's first calculate the PDF of the denominator random variable. Let's say we call it as q. So to calculate the denominator random variable, we must know the distribution of this random variable y. And for those who are not familiar with chi-square distribution, it would be good to know that chi-square distribution with n degrees of freedom has the same distribution as gamma distribution with parameters n by 2 and half. So in general, a gamma distribution with parameters n and lambda has the following distribution: x raised to n minus 1, e raised to minus lambda x, lambda raised to n, gamma n, where this denotes gamma function. So now to calculate the t distribution, let's first calculate the distribution of this variable, random variable q. And for that we'll use the Jacobian method. So let's go through these steps one by one. So first we assume that q is root y by n, then we express y in terms of q, then we take the derivative of that and we get 2nq. Then the distribution of q would be given by fq is equal to the distribution of y into Jacobian, which will be del y by del q. And we should understand that since this is root of y by n, q can always take positive values, hence this distribution is valid for all input values such that q is greater than 0. So since we know that gamma distribution with parameters n and lambda is distributed as follows, as we discussed above. So gamma distribution with parameters n by 2 and half would be distributed as follows: half e raised by n by 2, e raised by minus 1 by 2, y raised by n by 2 minus 1, gamma n by 2. So to calculate the distribution of q, we will replace the value of y from here in this variable. So we can see that y is nq square, so we'll replace this by nq square, and we'll replace this value by 2nq as we calculated above. So replacing these values, we get the following expression. So replacing these values, we get 1 upon 2 raised by n by 2 gamma n by 2 e raised by minus, we replace nq square by y, and then we replace y by nq square to get this expression, q raised by n by 2 into n into n by 2 minus 1, and then we multiply by del y by del q, which is 2nq. So which gives us the final expression for fq to be this: n raised by n by 2 divided by 2 raised by n by 2 minus 1 comma n by 2 e raised by minus nq square by 2 q raised by n minus 1. So now this is where things get little untidy. To calculate the distribution of the random variable t, which follows our t distribution with n degrees of freedom, we have to calculate distribution of x upon root y by n, and we assume root y by n to be random variable q, and we already have calculated the distribution of the random variable q to be this. And let's say for calculating the distribution of t, we also, let's say, assume a new random variable u whose distribution is q. So we have two unknown random variables u and t, and we have two known variables x and q. So u and t are unknown variables and x and q are known variables. X is normally distributed with random variable with the mean 0 and standard deviation of 1, and we know the distribution of q from here. So now we calculate the Jacobian, which is del x by del t, del x by del u, del q by del t, del q by del u, determinant of this matrix, which comes out to be u. So now we calculate the joint probability density function for our unknown random variables t and u, which would be the product of three terms, that is PDF for x, PDF for q, and our Jacobian u. And from this joint PDF, we have to calculate the PDF of t, which is actually our t distributed random variable. So to calculate the PDF of t, we'll simply marginalize the u using this formula, ft is equal to f of t comma u du. So if we integrate out u, we can calculate the distribution for t. So now let's try to put these terms one by one. Fx is simply a normally distributed random variable with standard normal distribution. So the PDF of fx is 1 upon root 2 pi e raised to minus x square by 2, which is this term. So instead of x, we replace x by ut as calculated here. So we get 1 upon root 2 pi e raised to minus u square t square by 2. And we have already calculated the distribution, the PDF for fq, and we simply replace the PDF of fq to be here, and we replace q with value u as calculated here, and we get this expression. Finally, we multiply it with Jacobian and we integrate this for the range of u, and since u is simply as q and q takes value from 0 to infinity, and hence the limits for this integration would be from 0 to infinity. So now to calculate this integration, we'll use variable change. So let's say we replace u square by 2 into t square by n by m, which implies u is equal to root 2m by root n plus t square, and if we calculate derivative of this, we get this. So now it gets a bit messy, but what we do is that we kind of bring out all the terms which are not dependent on our new integration variable m. So we bring out root 2 pi from this integration, from this term of du. We bring out root of n plus t square. We bring out 2 raised by n by 2 minus 1. We bring out gamma n by 2. We bring out n raised by n by 2. Then we integrate from 0 to infinity. This terms changes to, so this e raised to power minus n square n u square by 2 and e raised to power minus u square t square by 2. These both combined changes to e raised to power minus m, and this root 2m comes from this, and what we have left is u raised to power n. So we simply put u is equal to root 2m by root of n plus t square raised to power n tm. Then further we just keep all the terms of m here. So this expression becomes e raised to power minus m, and m raised to power n by 2 here, and m raised to power n by 2 minus n by 2 yeah, so m raised to power n by 2 here, and here we have m raised to power 1 by 2, which becomes m raised to power n minus 1 by 2, which can be written as m raised to power n plus 1 by 2 minus 1. And the way we are writing this, because this expression is simply our gamma function, and the value of this is gamma n plus 1 by 2. So, and now we bring other terms out of the integral. So we can see that root 2 raised to power n by 2 raised to power n by 2 and 2 raised to power n by 2 cancels away from here, and we have a root 2 here and a root 2 here, which gives an extra power of 2, which cancels out this one. So the terms, all the powers of 2 cancels out. What we are left with is root pi from here, and n plus t square, we have n plus t square raised by n by 2 from here and 1 by 2 from here, which gives us 1 plus n plus t square, 1 divided by n plus t square raised by n plus 1 by 2, and n raised by n by 2 divided by gamma n by 2. So if you spend a few minutes on this, you'll get to this expression, and after that we just simply take n common from this term so that it cancels with n raised by n by 2, and we merge one of the n's with pi to get this final expression. So this is the final expression, and the domain for this is minus infinity to infinity. Since t is x upon root y by n, where x belongs to minus infinity to infinity and denominator is positive, hence t takes values from minus infinity to infinity. So this is the probability density function of a t distributed random variable with n degrees of freedom. Now let's try to calculate the mean and variance for this distribution. So the mean of the random variable t is simply given by integration of t ft dt, which will be equals to integration of minus infinity to infinity gamma n plus 1 by 2 gamma n by 2 root n pi 1 plus t square by n raised to minus n plus 1 by 2 t dt. So this integral, let's say this function is gt, and we can see that if we replace t by minus t, that is g of minus t is simply minus of gt. Since this t will become minus t, everything else will remain same. G of minus t is minus gt, hence gt is an odd function. So the property of odd function is that it is anti-symmetric about origin. So if graph is something like that, when t is greater than 0, so graph would be something like that when t is less than 0. So this integration, the areas will cancel out and integration would come out to be 0, hence expected value would be 0, and which we can see from the curve also, like which we could see from the curve of the t distribution that it is centered at 0 and it's symmetrical both sides. So now let's calculate the variance. So variance of t is expected value of t square minus expected value of t whole square, and this comes out to be 0. So variance is simply expected value of t square, which is equal to t square ft dt minus infinity to infinity. So this comes out to be the same expression here, except that this t is replaced by t square. So if we replace this t by t square, I'm just saving my time and not writing this here again. So if we replace this t by t square, then this is an even function, and for even function we can write this integration to be 2 times 0 to infinity gamma n plus 1 by 2 gamma n by 2 root n pi. And let's also make a substitution. Let's substitute t square by n to be equals to some arbitrary random variable, let's say p. So then t would be root np, and dt would be 1 upon 2 root n upon p dp. So replacing these values, we get 1 plus p raised to power minus n plus 1 by 2, and t square means np, and dt means 1 upon 2 root n by p dp. So here we could cancel root n with root n and this 2 with 2, and we would split this 1 plus p into two parts. So this is 1 upon 1 plus p raised to n plus 1 by 2. So 1 upon 1 plus p raised to power 1 by 2 is divided here, and 1 upon 1 plus p raised to power n by 2 is divided here. And we just write 1 upon 1 by 1 plus p raised to power n by 2 in this form. And you'll just realize why we are doing this. And this root p cancels out, and we get a p raised to power 1 by 2. So we get this expression. So getting this expression is a bit tricky, but now we can make one more substitution. We can replace p upon 1 plus p with another variable. Let's say any variable r. Then we'll get this integration to be 0 to infinity gamma raised to n plus 1 by 2 gamma raised to n by 2 root pi, and so this is root r, and this is 1 minus r raised to power n by 2, and this implies p is equal to r plus pr, which implies r is equal to p is equal to r upon 1 minus r. So dp would be equals to 1 minus r square, 1 minus r, derivative of r is 1 minus r minus 1 dr. So this is simply derivative of p with respect to r. So which is equal to 1 upon 1 minus r whole square. Now r is, as p is from 0 to infinity, r is from 0 to 1. So p is 0, r is 0, but when p is infinity, r would be 1, because r is basically 1 upon 1 plus 1 by p. As p tends to infinity, this tends to 0, so r becomes 1. So these limits changes from 0 to 1. And this expression basically becomes to be gamma n plus 1 by 2 gamma n by 2 and root pi integration 0 to 1 r raised to power 1 by 2 1 minus r raised to power n by 2 minus 2 dr. So this is basically a beta function. So this function is a beta function, and beta 3 by 2 comma n by 2 minus 1, and hence we are just close to getting our final answer. 2 pi gamma n by 2 and upon root pi, and we can write this beta function in terms of gamma, which is equals to gamma of a plus b, which is n by 2 minus 1 plus 3 by 2, which is n by 2 plus 1 by 2 n plus 1 by 2, and this would be gamma 3 by 2 and gamma n by 2 minus 1. So which gives our final expression to be, so this simply becomes 1 by 2 gamma 1 by 2 upon root pi gamma n by 2 and n and gamma n by 2 minus 1. In fact, we can write this gamma n by 2 to be n by 2 minus 1 gamma n by 2 minus 1. And now we have reached to our final answer. So gamma half is same as root pi, and we cancel this out, and what we have left with is n upon n minus 2, which is our final answer. Hooray! I know it was a lot of hard work and lot of mess, but we finally reached our expression for the variance of T distribution with n degrees of freedom. So I hope you like this video, and more videos will be coming soon, and I keep my videos to be pretty detailed so that even people with preparing for high level details can get benefit from these videos. So please share these videos with your friends, subscribe, feel free to comment any of the suggestions, and stay tuned. Goodbye.